A very important part of calculus is a firm understanding of functions. Functions are a tool for describing the real world in mathematical terms. We often see functions in the form of an equation, a table, or a graph. Occasionally you also see those as a verbal description or as an arrow diagram. Remember the definition of a function. A function f from a set D to a set y is a rule that assigns a unique single element f of x that's an element of y to each element x that's an element of the domain. The most important part of this definition is the word unique. Each element in the domain corresponds to exactly one element in the range, a single element in the range. This picture shows an arrow diagram representation of a function. You'll notice you have a set D, and each element in D is mapped to exactly one element in set Y, which is your range. It's important to note that there are two values in the domain that go to the same value in the range, and that's okay. What would keep this from being a function is if any element, say A, were mapped to more than one element in the range. So if A also corresponded to f of x, then this would not be a function. But in order to be a function, each element in the domain must map to exactly one element in the range. When we think about graphs, the value f of x is the same as y. It's the height of the graph above the point x or below x if f of x is negative. For example, if you look at 1, the value f of 1 just corresponds to the y value at 1, or the height of the graph above the x-axis. Notice here where f of x is actually a negative value, it is the distance below the x-axis, between the x-axis and the graph. When we graph functions, for example, if we take y equals x squared and graph it over an interval from -2 to 2, we can do that by selecting x values in the interval and computing the y values. For example, if we plug -2 in, -2 squared is 4, or if we plug in -1, -1 squared is 1. We can choose any x values we want. Normally we choose mostly integers if possible because those will be the easiest to calculate, but you can see here that 3/2 has been chosen and 3/2 squared is 9/4. Once we create the table, then we can plot the points and draw the graph. The graph to the left is the graph of y equals x squared. The points have been plotted and a smooth curve has been drawn through those points. Notice that it is a smooth curve as opposed to the graph in the middle or the graph to the right, which are not the graphs of y equals x squared. The study of calculus will help us to understand why our graph looks the way it does as opposed to looking the way it looks in the middle or to the right. If we want to determine from a graph whether or not we have a function, we can apply what's called the vertical line test. What the vertical line test says is that no vertical line can intersect the graph of a function more than once. If a vertical line does intersect a graph more than once in any place, that graph is not the graph of a function. For example, if you look to the left, we have a circle. You'll see the red line that's drawn through the circle intersects the graph in more than one place. So that circle is not the graph of a function. However, the semicircle in the middle and the right, those are both functions. No matter where you draw a vertical line through either one of these graphs, it will never cross more than once. Another important concept dealing with functions that we'll see later on in calculus is the concept of increasing and decreasing. A function f is said to be increasing on an interval if f of x2 is greater than f of x1 whenever x1 is less than x2. What that means is, as your x values increase, your y values increase. In everyday terms, that just means that the graph is going uphill. F is said to be decreasing on an interval I if f of x2 is less than f of x1 whenever x1 is less than x2. What that means is as our x values increase, our y values decrease. Or in everyday terms, our graph is going downhill. If you look at this graph, this function is decreasing from -infinity to 0. Between -infinity and 0, our graph is going downhill. It's increasing between 0 and 1. It's going uphill. And from 1 to infinity, it's neither increasing or decreasing. It's just flat. That's often called being constant. Some other terms you'll see through the book is even function and odd function. If a function is even, then f of negative x is going to be equal to f of x. If a function is odd, f of negative x is going to be equal to negative f of x. And that's for every x in the function's domain. Here's an example of an even function and an odd function. Y equals x squared is an even function. Remember we said f of negative x is equal to f of x. And you can see here at negative x and at x you have the same y value. Visually what you can tell about even functions is that they're symmetrical about the y-axis. The graph at the bottom, y equals x cubed, is an odd function. What that means is for f of negative x would be equal to negative f of x. So when we have the opposite x value, we also have the opposite y value. That means that this graph is symmetrical about the origin. One thing to remember, we'll be talking about translations later. When you add a constant term to a function, like y equals x squared, the resulting function y equals x squared plus 1 is still even, because it's still going to be symmetrical about the y-axis. However, when you add a constant term to an odd function, like y equals x plus 1 is no longer odd. The symmetry about the origin is lost.